So here the fifth problem. A wheel of radius 20 centimeters has forces applied to it. The net force produced by the forces that is with respect to the center is. So in this case, so I draw that figure. So that figure will be given like this. Now in this case, that is a wheel of radius 20 centimeters. So this is also problem based on the moment of force. Now here these are the forces. Now this is taken as the A. And the force passing through that A is that is the 8 newtons of the force is there, and this is the A. And here this is the another force is there, that is passing through the O, that is the center of that. So that is O is here, and in this case this is the D, 6 newtons of the force, it is the D is here. And when you are coming to that another force, A and again the D, and this is the B. So this force is the B is here, and its force is the 4 newtons only. And thereafter it is the 9 newtons is here, and that force is that is the C. It is here, it can be taken as a C is here. Now you are given that information that is the 8 newtons is there, and 6 newtons and 9 newtons. Thereafter it is the 4 newtons. And in addition to that, you are given the radius of that wheel also. That radius of that wheel is the 20 centimeters is there. Now what is the net torque produced by the forces with respect to the center? Net torque produced by the forces means, so one by one we are coming. So first of all, A, that is the torque produced due to the A, that is the tau A. It is the force into perpendicular distance. So that's why this is the force. And here the perpendicular, this is the R, that is the radius is given, it is the R, and the perpendicular distance is nothing but here in this case. So this is the force is here, and now it is the perpendicular distance is here, and you are given this angle also. That angle is given here, that angle is 30 degrees that you are mentioned. So now that's why it is you are given, it is the 30 degrees is also there. So now it is the 30 degrees is there, and again it is a small r, and we consider this is the perpendicular distance. For this force of 8 newtons, this is the perpendicular distance about the point O. Because you are going to find out the moment of force, you are going about the center only. So that's why it is the about the O. This is the perpendicular distance. We name it as the X. So you have to find out that perpendicular distance first. So that perpendicular distance is a sine 30 we are taking, and for that sine 30, that is the opposite side, and again here it is taken as the 90 degrees will be here like this. So that's why X by R is here. So that is the X by R is here, and X is equal to sine 30 is the 1 by 2, and X by already that radius is also given. That radius is nothing but the 0.2. So that's why 0.2 meters is there. That is the 0.2 meters. And that's why it is the X is equal to 0.1 meter, which is nothing but the perpendicular distance of the force 8 newtons about the center O. So that's why torque A is equal to, that is the force is the 8 newtons, and it is the perpendicular distance is nothing but, so we write the formula also. So it is the FA into X is there. It is the 8 newtons, and again that perpendicular distance is nothing but the 0.1, and it is a 0.8 Newton meter. It is a 0.8 Newton meter, and again we have to give that direction also. So now this force is about the point O, means it is developing the torque in this direction. So that is nothing but the clockwise torque. So it is the clockwise. So that's why it is the clockwise torque is produced here. So like this, now it is moving like this, and again it is about the point O. So it is the clockwise. And when you are coming to this torque B, so that is the for this force, that is where that B is here, and this is the tangential. This force is the tangential. And about the point O, that is nothing but a passing through the center, this becomes the radius. So this is the radius. Now any radius that will be normal to the tangent. So that's why here the 90 degrees is maintained. Here the 90 degrees is maintained. So that's why it is a B is here 4 newtons. So that is a perpendicular distance is nothing but the R. So now here also FB to be taken, and again its a perpendicular distance is nothing but the R, because it is a tangential, and this is a radius which is normal to the tangent. So that's why FB into R. So for that we are taking it is a 4 is here, and already we know that is a 0.2. So it is a 0.8 Newton meter, and here it is, this is also this force about this point O, now it is like this. So that's why it is the anti-clockwise. So it is the anti-clockwise movement. So that's why anti-clockwise movement is taken, that is the torque B is cleared. Next here, now it is the torque C we are coming. This is the torque C. This is also tangential. Torque C is also tangential. So that is the force C is also producing that tangential. So in this case also, it is the Fc into R is there, and it is a 9 newtons and it is a 0.2. So it is a 0.8 Newton meter, and this is the, so it is like this. That's why, so once again I tell you, now it is the anti-clockwise like this for that B, and again this is the, so it is the clockwise. So it is a clockwise to be taken. So it is the clockwise, and thereafter it is the 0.8. So everything is come, that is the torque D. So once again I tell you, it is 8 into 0.8 torque A. Torque A is equal to sin 30. We have taken 0.8 Newton meter clockwise, and the torque B is here like this. And the torque D. So for this, this is the given that, that is the so it is the first again, once again I check you all these. So that is the force into perpendicular distance. Sin 30 is equal to x by r is there, and 1 by 2, that is the x is equal to 0.1 meter, and here the force is taken like this. So it is the 0.8 Newton meter, that's over. And after that, when you are coming to this one, that is a 4 into 0.2, 4 newtons is there, and again the 0.2. So it will be the 0.8 Newton meters, that is also over, and this can be taken as the 1.8. So 1.8 Newton meter is here, and when you are coming to this D, so D means that is passing through the center, and this is a torque due to the D, that is passing through the center. When it is passing through the center, that's why it is not at all maintaining any perpendicular distance. When it is not at all maintaining any perpendicular distance, in that case, it is the force D is here, and again into, that is the R will be taken as the 0. So that's why it is the 0 is here. Now all these forces together, they are producing the 3 torques only. One is the 0.8 Newton meter clockwise, and here also that is a 0.8 Newton meter anti-clockwise. So that's why they will be cancelled. So both are producing the torques which are equal in magnitude and opposite direction. So that's why both are cancelled. Only that net torque will be this one only, that is a 1.8 Newton meter, that is the clockwise to be taken. So therefore torque is equal to, that is the torque C, it is a 1.8 Newton meter clockwise. This will be the answer. So here only a small difficulty is in finding the perpendicular distance for this force about the point O, and the remaining are simple. Only this one only. So that's why you are getting this is a 1.8 Newton meter clockwise. That's all. So this problem also completed. So now it is, we are coming to the next problem. A circular hole of diameter r is cut from a disc of mass m and radius r. So that's why this is slightly difficult problem. So now this is the disc of a circular hole of diameter r is cut from a disc of mass capital M and the radius r. Suppose we consider this, the disc is here, and its mass is the m is here, and again this is the r, that also to be taken, r is here. Now it is the circumference of the cut passes through the center of the disc. So that's why this is the cut portion. This is the cut portion which is passing through the center of the disc like this. So that's why center of the disc means, so according to that given data, because you are not given in this figure, you are not given the figure, and you won't be given that figure even in your exam also. That's why from that given data, you have to draw that figure. It is given a circular hole of diameter r is cut from A, that is a disc of mass m and the radius r. So radius r is taken, and again this can be taken, diameter is r means its radius is the r by 2 is here. This can be the O, and this is taken as the O dash we consider. It is the O dash, that is through the center of the disc, the mi of the remaining portion of the disc about an axis perpendicular to the disc and passing through its center is. Now you are supposed to find out the moment of inertia about this O. You have to find out the moment of inertia. So that is the mi of the remaining portion of the disc about an axis perpendicular to the disc and passing through the center is. Suppose if at all such disc is there, and again some portion is cut here, and for that remaining portion you have to find out the moment of inertia about this O. And here that's why you have to find out the two moments of inertia. One is the moment of inertia of that entire disk, and that is moment of inertia of that entire disk, and for that you already know that is nothing but the I1 is equal to, it is the mr square by 2. So it is the I1 is equal to mr square by 2. And the second one is moment of inertia of this one alone. So that is the removed part, removed disk alone. So for that you have to take that I2. That is only the slightly difficult to find out that I2. After finding this I1 and I2, now you have to take that I1 minus I2, which indicates the moment of inertia of the remaining portion of the disk about the O. About the O. So once again I tell you. So first of all, this is the moment of inertia of that entire disk. That is in that case, so without considering that hole, so that's why that there is no such hole. So I1 is equal to mr square by 2 in that case. And again for this, when you are coming to this I2 is the moment of inertia of that removed portion of the disk, removed portion of the disk about that is the about the same center O. Now it is the I2 is here. That I1 minus I2 that indicates that is the moment of inertia of this I1 minus I2 that indicates moment of inertia of this remaining portion of the disk about the O. So I1 is equal to mr square by 2, that is over, that is cleared. So that's why it is taken as the first equation. And the problem is here only. And in this case, there are the, you have to apply that parallax theorem. And first of all, that is the parallax theorem means now one axis is here and another axis is also here like this. That's why two axes are appearing. So when these two axes are appearing, one axis is here and another axis is also here. These two axes are appearing, but you are supposed to find out the moment of inertia about O only. And for that, this is the I1 is for the total disk. So for this total disk moment of inertia. And I2 is the for removed portion of the disk, for the removed disk, for removed disk. That is the moment of inertia. And here I2 is equal to, now it is nothing but that is the IO dash. IO dash, and that is nothing but it is the moment of inertia of about its own natural axis, that is the INA we can take, that is the INA plus, and again it is the, for this it is the mass cannot be the m, it will be the m dash. And similarly the distance of separation is nothing but, the distance of separation is very simple, it is nothing but the r by 2 only in between these two axes. So once again I tell you, it is the for the removed disk, it is the I2 is equal to, here you have to apply that parallax theorem because the two axes are appearing. As I already told you, one is here and another one is here. You are supposed to find out the moment of inertia about this axis only. In this case, I2 is equal to INA. INA means this one, and for this m dash r square. M dash r square means this is the removed portion. So for that removed portion we consider its mass is the m dash. So that's why m dash r square is here. Now here you have to find out the INA. INA, now how it is possible? This also to be taken as the m dash and again the r square. So it is the r square, r dash square by 2. M dash r dash square by 2, that is to be taken. And again the plus m dash r square. R square means it is the r by 2 whole square, that is also there. Once again I tell you, it is the INA is equal to mr square by 2 is the general formula, but here the mass is there, that's why it is the m dash is here, and again it is the mass will be different, it cannot be the same value. M dash is here and again the r dash square is here by 2, and thereafter m dash r by 2 whole square is here. Now we have to find out the relation between that m and m dash. You have to find out the relation between that m and m dash. How it is possible? That is the, for the complete disk it is the mr square. Now so for the pi r square is taken, and after that that is the thickness is given, the thickness will be the same, and for that it indicates the mass is the capital M. It indicates the mass is the capital M. And for that in the second case it is the pi r by 2 whole square is there, and again the same thickness is there, and for that what will be the mass? So once again I tell you, it is the pi r square and again the thickness. Now for this the pi r square and the thickness. So or you can take that thickness is the common factor. That's why you can remove this thickness also. For the pi r square, its corresponding mass is the m. And for the pi r by 2 whole square, and its corresponding mass will be, so that's why it can be taken as the m dash is equal to pi r square by 4 by pi r square is here. And that becomes m dash is equal to m by 4. M dash is equal to m by 4. So one point is cleared. M dash is equal to m by 4. So that's why here it is the m dash is equal to m by 4 to be taken, and r dash is equal to r by 2 whole square is there, and by 2. R dash is equal to r by 2 whole square by 2, and m dash is equal to, again it is the m dash is equal to m by 4. Already the distance separation between these two is the r by 2. So that's why it is the r by 2 whole square is there, r square by 4, and that is the I2 is also there. I1 is there and I2 is there. This is the first equation, this is to be the second equation. And now moment of inertia of that removed portion of that is the removed portion of that disk is here. Now the moment of inertia of that remaining disk only. Therefore, mi of remaining disk, that is the I is equal to I1 minus I2. When you are taking that I1 minus I2, that will be the I1 is equal to mr square by 2, and this becomes mr square by 4 into 4 by 2 is here. So that's why mr square by 2 minus, that is the, this one also total to be taken, that is the mr square is here by 4 into 4 16 by 2 32 is here, and thereafter it is the mr square by 16 also to be taken. Then you get that required answer. Then you will be getting that answer. That answer is that is 13 mr square by 32. So it will be the 13 mr square by 32 will come. So in this type of problems are simple. It is the I1 is there, that is for the total disk, and the removed disk is there. Only you feel some difficulty in finding the moment of inertia of that removed disk, because the mass will be different value, and radius also will be a different value, and the distance of separation also that you have to find there. And for that mass it is a simple one, that is the pi r square is the area, and for that pi r square its corresponding mass is the m, and for the pi r by 2 whole square what is its corresponding mass? This will be the m by 4. You have to apply that m by 4 here, and in place of the r dash r by 2 whole square is there, by 2 will be as usual. So when you are solving, mi of that remaining disk will be that I1 minus I2, it is a 13 mr square by 32. So here, so far we have completed some of the problems here, and in next class also we continue the same models. So we continue the sum of those problems, and different models we can take. And here in the next class it is a continuation of the problems on the Torck, and again the parallel and perpendicular theorem, and again this moment of inertia. And after the completion of all these models only, then only we go to the conservation of angular momentum and velocity and time and acceleration of that rolling bodies. That's all.